right, so let's start with the first alternative method, subset selection. So as we said, subset selection basically says, okay, you have P equal to 100 predictors. We're going to choose the most important predictors and then fit the least squares using those most important predictors, right? We're not going to use all 100. We're just going to choose the most important. How do we do subset selection? That's a very important question. What we can do is we are going to use what is called best subset selection. So best subset selection, right? Best subset. That's what we want. We want the best subset. So to perform this selection, we are going to fit a separate least squares regression for each possible combination of predictors. Let's see the steps that are involved in this. It's easier to explain when we are dealing with the steps. So step number 1, what we're going to do is we have our p predictors, right? Let's say we have our p predictors. Let's just say 10 or 100, whatever it is. What we're going to do is, so our predictors are x1, x2, x3, x4, all the way up to x9 and x10. Those are the predictors that we have, right? So what we're going to do is, step number 1, we're going to have, let m naught be what is called the null model. It is called the null model, right? And the null model, it doesn't have any predictors. So it is y is equal to beta naught. That is the one that we have. Y is equal to beta naught does not have any predictors in it, right? And then step number 2 is for k equal to 1 to up to our p. In our case, our p is equal to 10. So for k equal to 1 to up to 10. So we're saying for each of these predictors, not like each of these predictors, but then we're just saying how many predictors we have. We have 10. So for 1 up to 10, what are we going to do? For 1 up to 10, first what you're going to do is you're going to fit all. I'm going to explain this. I'm going to explain this part. PK models. We're going to choose K models that contain exactly K predictors, and call it MK. Call it MK, right? We're going to call it no, we're not going to call it MK. We're going to fit we're not going to, yeah, cool. That is K predictors. What does that statement mean? Let's discuss what that statement means. When our K is equal to 1, basically we are saying when K, because we're saying for K, this is like a for loop, right? So it starts with 1, does the steps, goes to 2, does these steps that we're going to discuss, and then 3, 4, 5, and stuff like that. So let's start with K equal to 1. When you're saying K equal to 1, we are going to fit all models that contain exactly K predictors. So 1 predictor. So we already have our y equal to b naught. So on top of this one here, we're going to fit all models that have 1 predictor. So it's going to be y is equal to beta naught. What we have? We have 10, right? So we have these predictors here, x1, x2, x3. So how many models can we come up with that have 1 predictor? We can come up with this model here, x1. Instead of having x1 as the predictor, we can have another model. So this is going to be first model. Second model, can say plus, let's say beta 1. But instead of having x1 as the predictor itself, we have x2 as the single predictor that we have. Or we can come up with another model, beta naught plus beta 1, x3. We use x3 instead. So we can come up with so many models, I think 10 models that have one predictor where k is equal to 1. So it's going to be beta naught plus beta 1 times and x10, right? Let's explain that again. This is a for loop. So we're saying for each of these k's all the way up to 10, right? We are going to fit all, you ignore this part here, for all, fit all models that contain exactly k predictors. And since it's a loop, this is a loop, we are starting with 1, k equal to 1. So we are basically saying fit all models that contain exactly one predictor. So which means we can take one predictor and fit a model. Take this one instead of the x1, fit a model. Take x3 instead of x2 and fit a model. So these are the models that we can fit. So we can fit all these models here, right? We can fit all these models here. Then the second step now, the second step inside this for loop, after we fit all these models, we're still doing k equal to 1. After we fit all these models, we now choose the model, choose the best model and call it mk, right? Choose the best model and call it mk. In our case, what defines best? The best model. We are going to compare these models that we have fit here. We're going to compare them, and in our case, since we are doing linear modeling, as an example, right? We're going to use either RSS or R squared. We're going to use RSS or R squared. So the one that is the lowest, since it's a linear model, the lowest RSS or the highest R squared will be our best model for this case. And then that model, we are going to call it mk. So in our case, we are going to call it m1. It's going to be m1. So we're going to say m1, which model is the best? So after we have fit k equal to 1 for one predictor, we fit all these models. And then we compare their RSS or their R squared. We compare the R squared. We'll be like, oh yes, this one here, that is x2. This model is the best one. We're going to call that our m1. We're going to call that our m1. So we put it on the side. We have our m1, right? And then we go to when k is equal to 2. Fit all the models, because here it's a for loop, right? Our for loop is ended. We now go back and it's now doing k equal to 2, right? It now goes to k equal to 2. K equal to 2. When k equal to 2, it's now saying fit all models that contain exactly 2 predictors. So someone will say, okay, my models are going to be the first model will be beta naught plus beta 1x1 plus beta 2x2, because this one has 2 predictors. And another person will, and then you can come up with all the models that have 2 predictors in them. So it will be beta 1x1 plus beta 2x2. Cool. Another model will be beta 1x1 plus beta 2x3. Beta 1x1 plus beta 2x4. Beta 1x1 plus beta 2x5. All the way up to 10. And then you change here, it's going to be beta 1x2 plus beta 2x3. And stuff like that. So all the models taking combinations of your predictors here. So you can take x1 and x2, or x1 and x3, x1 and x4, x1 and x5, x1 and x10, or x2 and x3, x3 and x4, so all that you can do, all those models that will be for 2 predictors. And you compare their RSS, you move on to the second one. After you've fit all those models that you can come up with, right? After you fit them, you then do the second part here. You choose the best model out of those k equal to 2 models. When you've chosen the best model using your RSS, the lowest RSS or the highest R squared, when you've chosen the best model, you call it M2. Out of those ones that came from 2 predictors, it's now called M2. Right? You do that for k equal to 3. K equal to 3, right? Okay, well, what is k equal to 3 going to say? K equal to 3 is going to say, okay, fit all models that contain exactly 3 predictors. So it's going to be beta 1 x1 plus beta 2 x2 plus beta 3 x3 as an example. So you might have a model like this: beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x3. That is one model. But then someone will put an x4 here instead of an x3, x5, x6, x7. They can change around all this as long as we are selecting from our space of models here. This is our model. This is our of predictors. I mean, so you can start with these three, or you can include x4 instead of x3, x5 instead of x4, and stuff like that. All the combinations that you can come up with, as long as it has k equal to 3, as long as the predictors are 3, k equal to 3, right? And you fit all those models for 3 predictors. After you're done fitting all those models, you choose the best model out of those, and you call it M3. So now you have your M3, which is the best model for that set, for the k equal to 3. And it's the best model depending on the RSS of that set. Which one is the lowest RSS, or which one is the highest R squared for that set that you have, right? For that set that you have. Cool. So now that you've done that part, you've done even k equal to 10. K equal to 10, you are just going to have one model. Only one model that we have. Fit all models that contain exactly 10 predictors. We have 10 predictors, so there's only one model that we have all 10 predictors. So you just fit that one, you calculate its RSS, you're just going to call that one the M10. So what you basically have, you now have M1, which was the best model from k equal to 1. You have your M2, which was the model for k equal to 2. So this one has 2 predictors. You have your M3, which was the best model when you fit the model with 3 predictors, all the way up to M9, which was the best model when you fit 9 predictors. And then you have your M10, which is the best model when you fit 10 predictors, right? So these are the M's that you have. So inside M1, you have a model with 1 predictor. Inside M2, you have a model with 2 predictors. Inside M3, a model with 3 predictors. Inside M9, 9 predictors. So these models, they have different sizes. They are different sizes, right? So we are going to do step number 3. In step number 3, you are then going to select the single best model among this M0. Oh yeah, I forgot to say this one here that is no predictor is called M0. It's called the M0. That is no predictor. It's called M0. So select the single best model among M0, M1, all the way up to your MP. In our case here, our MP is just going to be M10 because we're 10 predictors, right? So we are going to choose the single best one now. Right? Which one is going to be the best of the best? The best of the best. Because these models here, they are the best for each k. For their k, they are the best. For their k, they are the best. But then now on step number 3, we are going to choose the best of the best. The best of the best model. Right? How do you do that? You are going to use cross-validation. We discussed that in the previous video. We are going to use cross-validation error, or you can use what we are going to discuss later. There are some methods we are going to discuss later. These methods are going, in this same chapter. In this same chapter, we are going to discuss this method. Something called the CP, or you can use the AIC, or BIC, or you can use the adjusted R squared. Adjusted R squared. We are going to discuss these. For now, just know that we use one of these methods to choose the best of the best. Why are we using these and not using RSS and R squared? We are using these methods here because these best methods, they have different variables. They have different variables. They are of different lengths. This one is of a variable k equal to 1. It has 1 variable. This one is 2 variables. This one is 3 variables. All the way up to 9 variables. It will be difficult to just use R squared and to use RSS and R squared when you are not comparing methods of the same length. Here we can use, in step number 2 here, We can use RSS and R squared because for each of the k, the models that we are comparing, they have the same number of variables. Like k equal to 1. All of the models that we are comparing with RSS and R squared, they have one variable. They all had one variable. So we can use R squared and RSS or RSS or R squared. We can use that because they had one variable. When k was 2, all of them that we're comparing here to choose the best one, they had two variables, two predictors. So we can use RSS or R squared. So it works, right? All the way up to k equal to 10. In that k equal to, let's say k equal to 5. K equal to 5. In that k equal to 5, when we're doing models with k equal to 5, all of them, they have 5 predictors. So we can compare them. We can compare them using RSS and R squared. But when we're choosing the best of the best, because now we are comparing mere models that have different lengths or different number of variables, we cannot use RSS and R squared anymore. So we are going to use these ones, these methods. They will help us choose the best of the best. Cool, we are going to see those methods later, but for now, that's what we're going to do. And we are going to say, oh yes, the best of the best is the M3. We already know what M3 is because we chose it. It was the best when we had k equal to 3. It was the best. So we already know what M3 is. Our M3 could be equal to, maybe y is equal to beta naught plus beta 1 x1. So these are predictions, but we can leave out the cap there. Beta, maybe beta 2, it might be the one with the x7 plus beta 3 with the x10. This one is part of M3. It came from it is the best of M3 that came from the set where k equal to 3, right? 3 predictors. I hope you understand this process here. So to solidify this reasoning here, to solidify the reason why we cannot compare our R squared when we have models that are like this, when we're comparing models of different number of variables. We know that our R squared and our RSS, R squared will always decreases as you add variables. That we know. R squared decreases as you add variables, right? As you add variables. R squared, RSS. Sorry, I was getting distracted because Siri thought I was activating her, but I wasn't. So I was talking RSS and maybe thought, I'm being activated. But anyway, RSS, we know that RSS always decreases as you add variables. So which means our M10 here, or the model with all the predictors, it will always have the lowest RSS. So if it's step number 3, when we are selecting the single best or the best of the best, we use RSS, we are always going to choose M10 because M10 will always have the lowest RSS. So we can use that because that one lies to us. It always decreases. It's always going to favor M10. Same with R squared. R squared always increases as you add variables. So as we add variables, it's always, if we are doing it at step number 3, it's always going to choose M10. It's always going to choose MP, the last model. It's always going to choose that because that is the highest RSS. So we cannot use it to choose the single best model or the best of the best. We cannot. We have to use these ones here. That is the other reason why we cannot use RSS at step number 3. All right. So this is what is called the best subset selection method. The best subset selection method. And as you can see, it's going to be computationally expensive because for each number of variables, we have to fit the models. And when we fit the models, we have to, after fitting the models, we have to then calculate the RSS and stuff like that. It's going to be computationally expensive. But before we go, let's see something here. Let's just plot something here. I think I still have space to just discuss this. So what we can do on step number 2. On step number 2, what we can do is, as we are doing the RSS, as we calculate the RSS, right? as we calculate the RSS, so you can plot the RSS with predictors, or we can plot the R squared. We can plot the R squared, and these are number of predictors. So number of predictors, right? Number of predictors. So this is going to be my R squared. What we can do is 2, 4, let's just say 2, 4, 6, 8, 10 in our case, right? 2, 4, 6, 8, 10 predictors. Cool. What we can do is we can say, all right, for each one of them, let's plot the RSS that is associated with. So for each, when our k was equal to 2, we can k equal to, so there's 1 here. So when k equal to 1, we can plot the RSS that are involved, that are associated with each of those models. So here we had k equal to 1, and then we will calculate the RSS for this one, because we have to choose the best model for k equal to 1, right? So we have to calculate the RSS. So we calculate the RSS for this one, RSS for this one, RSS for this one. We can have our RSS like that and plot them. So for each of the models that are k equal to 1, we can plot their RSS like that. Same applies when we have k equal to 2. We can plot their RSS. K equal to 3, plot their RSSs. K equal to 4, their RSSs. 5, 6, 7, 8, 9, 10. We're just plotting their RSSs. For k equal to 10, plot the RSSs of the models that have k equal to 10. Yeah, it's just going to be one model. It's just going to be one model, right? The same applies for R squared. We can plot the R squared for when k equal to 2, 4, 6, whatever it is. Plot the R squared that we would have calculated for each of the models that fit in that set. K equal to 8 set, plot their R squareds. Their R squared. What you're going to find is this. Your R squared is going to go down like that. Your R squared is going to, your R squared. So actually, these values will not be there. These values will not be there. What you find is, you find a pattern that is like this. And for your R squared, so this will not be there. You're going to find a pattern like this. Something like this. That's what you're going to find. That's what you're going to find. Because your R squared always increases and your RSS always decreases. It always decreases like that, right? Say for some few increases here and there, just a minor bumps and minor dips, but otherwise it decreases like that, right? So you're going to, what you see is these lines, they connect the best models. They connect the best models for each model size. So for when k equal to 1, this will be the best RSS. And then with size equal to 2, this will be the best RSS. So these lines that you plot here, you see that they connect the best methods for each, the best models for each model size according to RSS and R squared. As the figures show, these quantities improve as number of variables increase, but from 3 level, like from level 3 or from level 4, or from 3 variable model or 4 variable model, there's little improvement in RSS and R squared as a result of additional predictors. So what we can conclude is, we can say, I think it is safe for us to choose M3. Because after M3, there's really not much difference in the RSS. You see, the RSS is not really changing much. We are not really gaining RSS. So we would choose M3 as the best model. That's what you can do if you are looking at it graphically like that, right? So same principles, they apply for logistic regression and other models. So the other models, they are ordered by something called deviance. You order by something called deviance. And the deviance is just basically defined as the minus, this is equal to minus 2 times the maximum likelihood. I think we discussed maximum likelihood when we did logistic regression. So it's just defined as minus 2 times maximum likelihood. So the lower the deviance, the better. So the smaller the deviance, the better. Because maximum likelihood, that's what we usually use in logistic regression. We want this to be as high as possible. If it's as high as possible, then we are happy. But because of the negative sign, it means the deviance has to be as low or as small as possible. As small as possible, then we are happy. That is the best model, right? This best subset, it is great, but it is computationally expensive, right? It's computationally expensive. The number of models that you need to fit, they increase with the number of p that you need to do. Imagine we are now doing all the way up to x and 100. So which means here our for loop is going to go to p equal to 100. So it means for k equal to 1, you fit all the models. All the models that have one predictor, it means you have 100 models that have one predictor. And then imagine how many models there are going to be when you're choosing 2 predictors out of 100 predictors. Actually, the number of models for each step is given by pk, which is just, some can write it as pk or p choose k. So here's going to be 100 choose 2. On your calculator, you have I think the symbol written NCR. So you can punch 100 NCR and then you put a 2. You see how many models you would have to fit for k equal to 2. For k equal to 3, you do 100 choose 3, 4, 5, 6, 7, 8, 9, 10. All those models. And for simplicity, for you to know how many models you need to fit in best subset selection, you would have to fit a total of 2 to the power of p models. 2 to the power of p models for all k's, from k equal to 1 to k equal to 100. K equal to 1 to k equal to 100. If we had 2, if our predictors were only 2, we'd do k equal to 1 and we'd do k equal to 2, right? How many models are going to be? So we have x1 and x2. When we are doing k equal to 1, we have a model that just has x1 and we have a model that just has x2. And then when so it's good. Yeah, it's going to be the one that is beta 1 x1, beta 1 beta. So it's going to be beta 1 for k equal to 2 is going to be beta 1 x1 plus beta 2 x2. And then we have our null model that just has beta naught. So we have our null model when our k equal to 0, the first one that we start off with, beta equal to naught, and then this one, these are the ones x1 or the one with x2 when our k equal to 1. And then when our k equal to 2, we just have that single one that is beta 1 x1 beta 2. So we have 1 2 3 4 models. So when our p equal to 2 is going to be 2 to the power of 2. So we'll fit a total of 4 models. In our case, when our p was equal to 10, we are approximately going to fit 1,000 models. So in this case here, we're going to fit 1,000 models. So imagine we're going to do 1,000 models, calculate their RSS, and then put them in their M's, and then do the AIC or the PIC, choose the best of the best out of those. It's going to be, so we're going to have the best of the best. We're going to choose from M0 all the way up to M equal to 1,000. So we're going to have 1,000 models. 1,000 models, 2 to the power of 10. It's approximately 1,000. Now imagine when we have 20, p equal to 20. We're going to do over 1 million models. So it scales up quite quickly. The computation required here scales up way quickly when we have many predictors. So best sub-selection, although it's fine, it works well, make sure that we don't make a mistake in choosing the wrong model, but it is computationally expensive. All right. So we are going to, in the next video, we're going to discuss other methods that are going to improve on this computation, or that are going to be computationally efficient, more efficient than this best sub-selection method. They are going to be stepwise selection methods. So stay tuned for that video.